So we're starting a new unit on quadratics, and this is going to be one of 2 units on quadratics. This is quadratics part 1. So you should be familiar with quadratics. You would have done quadratics in grade 10. So we're just going to kind of pick up where you left off from grade 10. So a lot of this will be review, but I'll definitely go over everything from scratch. So most of this node is already filled in. So I'm just mostly going to talk through it. And this, you don't really need to know how to do this. This is just mostly an introduction to quadratics and a reintroduction to parabolas and maybe some scenarios where you might see something like that. So for example, below are the details regarding the ticket price of an amusement park. So a group of 20 costs $40 per person. So if a group of 20 costs $40 per person, the amount of revenue that's going to be made is $800. For every extra person, you get a $1 less per person cost. So for example, if 21 tickets are bought, then you only have to pay 39 each. And in this case, the amusement park is going to make $819, 21 times 39. So for groups below 20, though, it's going to cost $1 more for each person. So for example, if it was a group of 17, then the tickets are going to cost $3 more. It's 3 people less, so the price is going to be $3 more. And the revenue for the amusement park in that scenario would be $731. So I've kind of showed it over here, again, kind of how this is working. 20 people is $40 is the baseline. So 1 extra person, the price goes down by $1. 1 less person, the price goes up. So what we want to know is in groups of 2 or 3, we want to decide the amount of visitors you feel would bring in the most revenue and then calculate the amount of revenue. So what I did is I had the class guess, like, tell me some guesses you think for the amount of people that would bring in the most money. Would more people bring in more money? Well, people guessed and they said, 25 people maybe 30, 35. What if we did 50 people, 10 people? So what I did was I took these amounts of people and then I had the costs that were associated. So this time I did 5 more people, so it cost $5 less. Here there were 30 people, which is 10 more, so the cost was $10 less. 35 people, that's 15 more people, so the cost went down pretty drastically. We thought, what if we brought in 50 people, which is a lot? Well, then the cost would have gone down by $30, down to $10. And then we thought, well, maybe let's try if we don't have a lot of people, like 10. So when that happens, the cost goes up to 50 because this is 10 below, so the price went $10 higher. So multiplying these prices times the cost, you get the revenues that went with them. So we had a variety of different answers. If we were just looking at our table values, then we can see that this one here gave us the most revenue. Now, we're not sure if that's the one that gives us the most out of all the possibilities, but what we're going to do now is put these on a graph. So again, according to the table, this is good coming from the table, but let's look at it at a graph. And I've already done the graph, but basically what I did is I plotted these points. So all the different number of people that we did on this page became a point. So when the number of people was 25, the revenue was $875. I put that on the graph. So here's 25 and $875. When we upped it to 30 people, we had revenue of $900. When we had 35 people, we had revenue of $875 again. When we had 50 people and it cost $10, the revenue was $500. And when we had 10 people, it cost $50, the revenue was also $500. So I plotted all the different points and then I just connected them. And if we notice the shape of this graph, if you remember from grade 10, it takes this shape, it kind of looks like an upside down U. It's a parabola. So this is a quadratic relation. And now we can go ahead and answer these questions. So in order to get the most money, how many people would attend the park? So ideally for the amusement park, you would have 30 people. The maximum revenue when these 30 people would show up, if I scroll across here, it would be $900. I can do some interpolation as well. What is the revenue from a group of 20? So I started at 20, went up on a dotted line to my graph, hit the point, moved over. I see that I would get $800. And then what happens at 60 people? Well, that's an interesting point, because if 60 people show up, then that means the price gets decreased by $40. But the original price was $40, so the price would be zero. So that's why the revenue is zero, because 60 people show up, but if the price of the ticket's zero, then they're not going to make any revenue. So price equals zero. And therefore, the revenue would equal zero. So this would not be a good idea for the amusement park. And then what would happen after 60? Does this make sense? Well, no, just because according to the model, if we start bringing more than 60 people, the prices of the tickets with the model that we talked about would go negative, which doesn't make sense in any world. The amusement park would not charge negative prices or give prices away. So the model kind of stops making sense towards that point. Would our revenue be negative, charge a negative amount? So it wouldn't make sense. So we're going to do another one of these, just a scenario where it's a situation and it turns out that it can be modeled with a quadratic. And this is kind of real world stuff, because just going back, I always tell this story when I was younger, and I always watched the Blue Jays and their baseball games, and I always wondered why the stadium was only half full, and I always thought to myself, well, why don't they just charge less for a ticket and then they'll sell out every game? That would be great. They'd get a sellout. But what I didn't realize at my young age was that they don't really care about how many people are in the stands. They care about how much money they're going to make. So I'm sure they have a mathematician on their staff that has determined the ideal price points that not necessarily bring in the most people, but would bring in the most money. So they're probably going to make more money selling 30,000 tickets at maybe like $50 each than if they filled the stadium and charged like $10 each. So there is that sweet spot that you're always looking for in these kinds of scenarios. So for this example, it's kind of similar to the last one we just did. This time it's involving selling watches. So if you're a watch salesperson, you have to decide how much to sell it for. And common sense tells us that the higher the price of the watch, the less we're probably going to sell. So what this person has determined is they set the watch price at $50. They establish that they probably sell around $80. But every time they increase it by $5, they're probably going to sell less, and in this case, 10 less. So if we go up to $55, we're only going to sell 70. So the question becomes, well, what price should I set the watch to make the most money? Not sell the most watches. I want the most money. Likewise, a $5 decrease in the price. So if I went down to $45, it's cheaper now. I'm going to end up selling a few more watches. So now I'm up to 90. But which of these combinations is going to give me the most revenue? So our job is to determine the price of the watch that's going to make the company the most money. So I have all the different prices of the watches here. This was the original 50 watches for $80. And then I filled in the table accordingly. So you can pause it to fill in this table if you want. But basically what's happening is every $5 increase in the price, I sell 10 fewer watches. Every $5 decrease in the price, I end up selling 10 more. And then I go price times quantity, and I get the revenue. And I'm looking for the one that gives us the most money. And it's not hard to spot. We've done pretty much every possibility here. And we see that when we set the price of the watch at $45 and sell 90, that's going to give us the most money. So the most money that can be made is $4,050, occurs at this price point. So like the last example, we're going to go ahead and put this on a graph. And again, I've already have this filled out. So I put in all the different price points and all the revenues that you would get with it. So the one that gave us the most here was the $45 price point with just over $4,000 revenue. 50 watches was 4,000 right on. 40 watches was 4,000 right on. And I just graphed them all from the table before. And just like last time, now that I have a graph, I can answer some questions. So in order to get the most money, what should the price of the watch be set at? We already established this, $45. Maximum revenue, already established, $4,050. What is the revenue when the watch is 75? So we're going to interpolate again. If I go to $75, go up to my graph and see that that would bring in revenue of $2,250. And what do you think would happen to the revenue if the price of the watches continued to increase? So let's think about this. What if I just kept increasing the price? Well, I highly doubt this graph is just going to make a U-turn and get more money. The revenue is going to continue to decline because as you charge more, less will be sold to the point probably where you're just going to raise the price so high that nobody's going to buy it and your revenue would end up approaching zero. So again, this lesson was short, and again, it was just a couple investigations and of applications just to reintroduce us to the idea of quadratics, what the graphs look like, and maybe what we're trying to accomplish by making these kinds of graphs, finding the maximums, finding the minimums. So there's a little bit of homework, number 1 to 5, on the next page that you can work on.